All of us have the experience of seeing a spark or hearing a crackle when we take off our synthetic clothes or sweater, particularly in dry weather. This is almost inevitable with ladies' garments, like a polyester sari. Another common example of electric discharge is the lightning that we see in the sky during thunderstorms. We also experience a sensation of an electric shock either while opening the door of a car or holding the iron bar of a bus after sliding from a seat. The reason for these experiences is discharge of electric charges through our body, which were accumulated due to rubbing of insulating surfaces. You might have also heard that this is due to generation of static electricity. Static means anything that does not move or change with time. Electrostatics deals with the study of forces, fields, and potentials arising from static charges. Electric charge. Many such pairs of materials were known which on rubbing could attract light objects like straw, pith balls, and bits of papers. There were only two kinds of an entity, which is called the electric charge. We say that the bodies like glass or plastic rods, silk, fur, and pith balls are electrified. They acquire an electric charge on rubbing. There are two kinds of electrification, and we find that like charges repel and unlike charges attract each other. The property which differentiates the two kinds of charges is called the polarity of charge. You know that all matter is made up of atoms or molecules. Although normally the materials are electrically neutral, they do contain charges, but their charges are exactly balanced. Forces that hold the molecules together, forces that hold atoms together in a solid, the adhesive force of glue, forces associated with surface tension, all are basically electrical in nature, arising from the forces between charged particles. To electrify a neutral body, we need to add or remove one kind of charge. When we say that a body is charged, we always refer to this excess charge or deficit of charge. In solids, some of the electrons, being less tightly bound in the atom, are the charges which are transferred from one body to the other. A body can thus be charged positively by losing some of its electrons. Similarly, a body can be charged negatively by gaining electrons. Conductors and insulators. Conductors and insulators. Those substances through which electricity cannot flow are called insulators. The presence of free electrons in a substance makes it a conductor. In this, copper wire are conductors and plastic cover is insulator. Same case is with 3-pin plug. Plastic case is insulator and metal pins are conductor. A metal rod held in hand and rubbed with wool will not show any sign of being charged. However, if a metal rod with a wooden or plastic handle is rubbed without touching its metal part, it shows signs of charging. Those which allow electricity to pass through them easily are called conductors. They have electric charges or electrons that are comparatively free to move inside the material. Metals, human and animal bodies, and earth are conductors. Most of the non-metals like glass, porcelain, plastic, nylon, and wood offer high resistance to the passage of electricity through them. They are called insulators. When some charge is transferred to a conductor, it readily gets distributed over the entire surface of the conductor. In contrast, if some charge is put on an insulator, it stays at the same place. This property of the materials tells you why a nylon or plastic comb gets electrified on combing dry hair or on rubbing, but a metal article like spoon does not. The charges on metal leak through our body to the ground, as both are conductors of electricity. When we bring a charged body in contact with the earth, all the excess charge on the body disappears by causing a momentary current to pass to the ground through the connecting conductor. This process of sharing the charges with the earth is called grounding of earthing. Earthing provides a safety measure for electrical circuits and appliances. Charging by induction. When we touch a pith ball with an electrified plastic rod, some of the negative charges on the rod are transferred to the pith ball, and it also gets charged. Thus, the pith ball is charged by contact. It is then repelled by the plastic rod, but is attracted by a glass rod which is oppositely charged. Basic properties of electric charge. We have seen that there are two types of charges, namely positive and negative, and their effects tend to cancel each other. If the size of charged bodies are very small as compared to the distances between them, we treat them as point charges. All the charge content of the body is assumed to be concentrated at one point in space. Additivity of charges. If a system contains 2-point charges Q1 and Q2, the total charge of the system is obtained simply by adding algebraically Q1 and Q2. That is, charges add up like real numbers, or they are scalars like the mass of a body. If a system contains n charges, Q1, Q2, Q3, and so on till Qn, then the total charge of the system is Q1 plus Q2 plus Q3 and so on till plus Qn. Charge is conserved. The total charge of the isolated system is always conserved. It is not possible to create or destroy net charge carried by any isolated system, although the charge carrying particles may be created or destroyed in a process. Sometimes nature creates charged particles. A neutron turns into a proton and an electron. The proton and electron thus created have equal and opposite charges, and the total charge is zero before and after the creation. Quantization of charge. All free charges are integral multiples of a basic unit of charge denoted by E. Thus, charge Q on a body is always given by Q is equal to NE, where N is an integer, positive or negative. This basic unit of charge is the charge that an electron or proton carries. Coulomb's law.
Coulomb's law in vector form. If Q1 and Q2 are the strengths of the two like charges separated by a distance r, then the force exerted by the similar charges on one another are equal and opposites. That is, vector F12 is equal to minus vector F21.
Coulomb's law is a quantitative statement about the force between 2-point charges. When the linear size of charged bodies are much smaller than the distance separating them, the size may be ignored and the charged bodies are treated as point charges. Coulomb measured the force between 2-point charges and found that it varied inversely as the square of the distance between the charges and was directly proportional to the product of the magnitude of the two charges and acted along the line joining the two charges. Electric field. Field of a point charge. In this animation, each arrow indicates the electric field, that is, the force acting on a unit positive charge placed at the tail of the arrow. Connect the arrows pointing in one direction and the resulting figure represents a field line. Let us consider a point charge Q placed in vacuum at the origin O. If we place another point charge Q at a point P where OP is equal to R, then the charge Q will exert a force on Q as per Coulomb's law. Electric field due to a system of charges. Consider a system of charges Q1, Q2 and so on till Qn with position vectors r1, r2 and so on till rn relative to some origin O. Like the electric field at a point in space due to a single charge, electric field at a point in space due to the system of charges is defined to be the force experienced by a unit test charge placed at the point without disturbing the original positions of charges Q1, Q2 and so on till Qn. Physical significance of electric field. Electric field is an elegant way of characterizing the electrical environment of a system of charges. Electric field at a point in the space around a system of charges tells you the force a unit positive test charge would experience if placed at that point without disturbing the system. Electric field is a characteristic of the system of charges and is independent of the test charge that you place at a point to determine the field. The term field in physics generally refers to a quantity that is defined at every point in space and may vary from point to point. Electric field is a vector field since force is a vector quantity. Electric field lines. Let the point charge be placed at the origin. Draw vectors pointing along the direction of the electric field with their lengths proportional to the strength of the field at each point. Since the magnitude of electric field at a point decreases inversely as the square of the distance of that point from the charge, the vector gets shorter as one goes away from the origin, always pointing radially outward. Electric flux.
Electric flux, the product of area dA and the component of electric intensity E cos theta normal to the area is the electric flux.
Consider flow of a liquid with velocity v through small flat surface ds in a direction normal to the surface. The rate of flow of liquid is given by the volume crossing the area per unit time psi ds and represents the flux of liquid flowing across the plane. If the normal to the surface is not parallel to the direction of flow of liquid, that is to v, but makes an angle theta with it, the projected area in a plane perpendicular to v is psi ds cos theta. Therefore, the flux going out of the surface ds is v dot n vector ds. Electric dipole. An electric dipole is a pair of equal and opposite point charges q and minus q separated by a distance 2a. The line connecting the two charges defines a direction in space. By convention, the direction from minus q to q is said to be the direction of the dipole. The midpoint of locations of minus q and q is called the center of the dipole. The field of an electric dipole. The electric field of the pair of charges minus q and q at any point in space can be found out from Coulomb's law and the superposition principle. When the point is on the dipole axis and when it is in the equatorial plane of the dipole, that is, on a plane perpendicular to the dipole axis through its center. Physical significance of dipoles. In most molecules, the centers of positive charges and of negative charges lie at the same place. But in some molecules, the centers of negative charges and positive charges do not coincide. Therefore, they have a permanent electric dipole moment even in the absence of an electric field. Such molecules are called polar molecules. Dipole in a uniform external field. Consider a permanent dipole of dipole moment P in a uniform external field E. We mean that P exists irrespective of E. There is a force QE on Q and a force minus QE on minus Q. The net force on the dipole is 0. Since E is uniform, however, the charges are separated. So, the forces act at different points, resulting in a torque on the dipole. When the net force is 0, the torque or couple is independent of the origin. Its magnitude equals the magnitude of each force multiplied by the arm of the couple. Continuous charge distribution. On the surface of a charged conductor, it is impractical to specify the charge distribution in terms of the locations of the microscopic charged constituents. It is more feasible to consider an area element, triangle S, on the surface of the conductor and specify the charge, triangle Q, on that element. Gauss's law. As a simple application of the notion of electric flux, let us consider the total flux through a sphere of radius r, which encloses a point charge q at its center. Divide the sphere into small area elements. Applications of Gauss's law. Applications of Gauss's law is the best understood by some examples. Field due to an infinitely long, straight, uniformly charged wire. Consider an infinitely long, thin, straight wire with uniform linear charge density pi. The wire is obviously an axis of symmetry. Field due to a uniformly charged infinite plane sheet. Let mu be the uniform surface charge density of an infinite plane sheet. Field due to a uniformly charged thin spherical shell. Let mu be the uniform surface charge density of a thin spherical shell of radius r. The situation has obvious spherical symmetry.